Welcome to Physics Hub. Today is 21st April 2019 Sunday, and here I am with a new set video. So you must be knowing it that we upload a set video on every Sunday, and it usually consists of 10 solved problems from different topics of physics. We generally upload the question paper on our Facebook page a little earlier so that you can try to solve the questions and match your answers when the solutions are uploaded. Now one thing, whenever we upload a video, we distribute it into different relatable playlists. So go through the playlist and you will be able to get videos as per your choice, and keep a track of our community posts as well. It will help you to make your base of physics strong. You can check the description section of this video to get useful links. Now without any further delay, let's start today's set video. So this is set 29, and this set contains 10 questions from capacitors. So the first question is, in the given circuit, a charge of plus 80 microcoulomb is given to the upper plates of this 4 microfarad capacitor. Then in the steady state, the charge on the upper plate of the 3 microfarad capacitor is. So let the charge on the 3 microfarad and 2 microfarad capacitors be Q and Q prime respectively. Plate of 4 microfarad charge on lower plate of 4 microfarad means in this plate, the lower one, capacitor is minus 80 microcoulomb, because you have given plus 80 microcoulomb on the upper plate, so minus 80 microcoulomb will be induced in the lower plate. Now lower plate of 4 microfarad capacitor and the upper plate of this 2 microfarad and 3 microfarad capacitor, these 3 plates form an isolated system. Hence net charge on this system must be 0. Therefore Q plus Q prime and this minus 80 microcoulomb, sum of them will be equals to 0. The potential V equals to Q by C across the 2 capacitors, 2 microfarad and 3 microfarad, are equal, which gives, because they are connected in parallel, so the voltage drop across them will be same. And using this formula V equal to Q by C, we get Q by 3, and it must be equal to Q prime by 2. Therefore from here we get Q prime equals to 2/3 Q. Now inserting this value into equation 1, we get that Q equals 2 to 40 by 5 means 48 microcoulomb, and that's what it asked you to find out, and it is matching with option C. So the charge on the upper plate of 3 microfarad capacitor will be plus 48 microcoulomb. You can check the calculation, it is correct, I think. Now question number 2, a 2 microfarad capacitor is charged as shown in the figure. The percentage of its stored energy dissipated after the switch S is turned to position 2 is. So this is the figure. We have named the capacitors, this capacitor as C1 and this capacitor as C2. Initially charge on the capacitor C1 is, so initially means when it is connected to switch 1. So charge on the capacitor C1 is Qi equals to C1 V, I for initial, and its electrostatic energy is Ui equals to Qi square by 2C1. Let the final after switch is turned to position 2, charges on the 2 capacitors be QF1 and QF2. Then the charge conservation gives you, means total charge must be conserved, so charge which was there initially and charge which is there finally will be same. So QF1 plus QF2 charge on these 2 capacitors will be equals to Qi initial charge on this single capacitor C1. Now the capacitors C1 and C2 are connected in parallel, thus the voltage across both the capacitors will be same. So as we have done in the first question, QF1 by C1 equals to QF2 by C2. Therefore QF2 equals to C2 by C1 into QF1. Now putting this value into equation 1 in the same way, we get QF2 equals to 4 by 5 Qi, and QF1 equals to Qi by 5. Okay. Now electrostatic potential energies corresponding to the final configuration is UF1 means electrostatic energy in the capacitor 1, and UF2 is electrostatic energy in the capacitor 2. Is we found Ui by 25 and UF2 equals to 4 by 25 Ui, where ui is qi square by 2c1. Okay, therefore the energy loss means the initial energy minus the total final energy. So initial energy minus uf1 plus uf2, so we have written them in terms of ui. So 1 minus 1 by 25 plus 4 by 25 into ui, so we found that it's 0.80 of ui, means 80% of ui, means 20% of ui is lost. Now comment down, why do we get this energy loss? Why 20% of this energy is lost? Comment down and we'll reveal the answer. Question number 3. Two identical capacitors have the same capacitance C. One of them is charged to potential V1 and the other to V2. The negative ends of these capacitors are connected together. When the positive ends are also connected, the decrease in the energy of the combined system is. Okay, so what we have to find out, so this is capacitor 1, this is capacitor 2, or both of having same capacitances, and the first capacitor is giving voltage V1 and the second capacitor is has been given the potential V2. Therefore initial charges on the capacitor will be Q1 equals to C into V1 and Q2 equals to C into V2. Initially total electrostatic energy stored in the two capacitors ui equals to half C V1 square plus half C V2 square equals to half C V1 square plus V2 square. Okay, maybe I am so speedy, so if you don't understand, pause the video and watch it again. Okay, now let Q1 prime and Q2 prime be the charges on the capacitors when the same terminals of the two capacitors are connected to each other. So as you can see, the negative terminal is connected to the negative terminal and positive terminal is connected to the positive terminal. The charge conservation gives you that the initial charge and the final charge should be same. So initially the total charge was Q1 plus Q2 and finally the total charge is Q1 prime plus Q2 prime. So they must be same according to the charge conservation law. The potential V prime across the two capacitors are equal because they are connected in parallel. So Q1 prime by C goes to Q2 prime by C. Therefore we can, as the capacitances are equal, so we can infer that Q1 prime equals to Q2 prime. Now putting this value into this equation, we found that Q1 prime equals to Q1 plus Q2 by 2. Therefore V prime equals to 1 by 2C into Q1 plus Q2, means V1 plus V2 by 2. Thus the final electrostatic energy stored in the two capacitors, this is the final configuration, and the final electrostatic energy stored in these two capacitor, means in this final configuration, is UF equals to half C V1 B prime square plus half C B prime square. Because both the capacitance as well as the potential difference are same here, so this is C V prime square, means, and V prime equals to V1 plus V2 by 2, so C into V1 plus V2 whole square by 4. So we just expanded it, V1 A plus B whole square, the formula we have used here, V1 prime V1 square plus V2 square plus 2 V1 V2. Now loss energy means UI initial energy minus final energy, and we found that it is equals to C by 4 V1 minus V2 whole square, and that's what it asks to you to find out what is the energy loss, means decrease in energy. It is half 1 by 4 C V1 minus V2 whole square. It is matching with option C. Option C is the correct option. Question number 4. The energy stored in the capacitor as shown in figure A is 4.5 10 to the minus 6 joule. If the battery is replaced by another capacitor of 900 picofarad as shown in the figure B, then the total energy of the system is. Okay, so this is the first configuration A and this is the second configuration B. So energy stored in the capacitor is found by this formula, Q square by 2C. Now Q goes to C into V. C is given 900 picofarad and V is given to be 100 volt. So charge is 9 into 10 to the power 8 minus 8 coulomb. Energy of the capacitor when fully charged is Q square by 2C and it is given to be 4.5 10 to the minus 6 joule. Now what happens if we replace this 100 volt battery with a 900 picofarad capacitor? The total charge is conserved. In figure B we see the total capacitance is C prime equals to 2C because it is connected in parallel, so the capacitors will be added, unlike to the case of resistances. means we got the total capacitance is 1800 picofarad. Therefore the final energy is q square by 2c prime, means 4.5 into 10 to the minus 6 by 2, because here c prime is 2c, so 1/2 factor will come and q square by 2c will remain, and q square by 2c is 4.5 into 10 to the minus 6, so half into 4.5 into 10 to the minus 6 means 2.25 into 10 to the minus 6 joule, and this is the final energy of the system, and it is matching with option 2. So option B is the correct option. Moving to question number 5. A parallel plate capacitor of area A, plate separation D, capacitance C, is filled with 3 different dielectric materials having dielectric constants K1, K2 and K3 and so on. If a single dielectric material is to be used to have the same capacitance C in this capacitor, then its dielectric constant K is given by. Okay, so the capacitance of a parallel plate capacitor of a plate area A and plate separation D and dielectric constant K is not this is separated. So dielectric constant K is given by C equals to epsilon naught Ka by D. Given configuration can be considered as a combination of 3 capacitors having capacitance K1, K2 and K3. The first capacitance C1 due to this dielectric K1 is epsilon naught K1, and the area is A by 2 here for this part. So A by 2, and the distance, this distance is D by 2, so this is also D by 2. So we just put D by 2, and we found K1 C0, when C0 equal to epsilon naught A by D. In the same way we found this capacitance of this section K2, we just replaced A by 2 and D by 2, and we found it is equal to K2 into C0. Similarly for this one C3, where the area is replaced by A and D is replaced by D by 2, we found it 2 K3 C0. The capacitors C1 and C2 are connected. This C1 and C2 are connected in series and C3 is connected in parallel. So C1 are connected in parallel with the effective capacitance C12 equal to C1 plus C2. The C12 is combined in series with C3. Okay, so these 2 capacitors are connected in parallel and it is connected in series with C3, and this configuration gives the effective capacitance of the 3 capacitors as C1 to 3 equals to C1 to C3 by C12 plus C3. After simple calculation we see it is equals to this term into C0. Okay, so if these 3 capacitors are these 3 dielectrics are replaced by 1, then what will happen? We get the effective dielectric constant K equals to 2 into K1 plus K2 by into K3 by K1 plus K2 plus 2 K3. And if we take reciprocal of this, we get 1 by K equals 1 by K1 plus K2 plus 1 by 2 K3, and it is matching with option B. So option B is the correct option. Moving to question number 6. 2 identical metal plates are given positive charges Q1 and Q2, where Q2 is less than Q1. If they are now brought close together to form a parallel plate capacitor with the capacitance C, the potential difference between them is. Okay, so this is a good question. So this is a A and this is B, and this is some other things, don't consider this. So this is the first plate, this is the second plate. A be the area of the plates and D be the separation between them. So E1 means electric field due to this plate 1 is sigma 1 by 2 epsilon naught, and the direction will be I cap. So these are positive plates, so the direction will be out of it. Okay, so E1 equals to sigma by 2 epsilon naught I cap, and E2 will be sigma by 2 epsilon naught minus I cap. Direction matters here. The resultant field E and potential difference between the 2 plates are E equals to E1 plus E2, means this is according to superposition principle, Q1 minus Q2 by 2 epsilon naught I cap, and the potential difference E into D, means this is the electric field into D, means Q1 minus Q2 by 2 into epsilon naught A by D. Now epsilon naught A by D equals to C, so Q1 minus Q2 by 2C, and it is matching with option matching with option D. Option D is the correct option. Question number 7. 3 equal capacitors each with capacitances C are connected as shown in the figure. Then the equivalent capacitance between A and B is. Now the given circuit can be redrawn as this. So this is in connect these 3 capacitors of equal capacitances are connected in parallel, so the effective capacitance will be the sum of the capacitance, means C plus C plus C equals to 3C. Now how we are getting this configuration, that is the question. So look, this is the first end. So in parallel combination we know that the one port is connected to one point and another port is connected to the other point. So for this first capacitor you see it is connected to A, and the second capacitor it is connected to B. Okay, so this one you got. For the next capacitor you see that this one port is connected to A and another port is connected to B. And similarly for C you see one port is connected to A and another port is connected to B. So effectively we are getting this configuration. So the effective capacitance is between A and B is 3C. Question number 8. The magnitude of electric field E in the annular region of a charged cylindrical capacitor is. Okay, so this is the cylindrical capacitor, the core axis of the cylindrical capacitor. Now we take a cylindrical Gaussian surface of length L and radius R. By symmetry, electric field is radial and is of same magnitude at all points at a radial distance R. The fluxes through the end surfaces A and B of the cylinder, these flat surfaces A and B, the fluxes through these end surfaces is 0. So the contribution of fluxes will come from these curved surfaces, and applying Gauss's theorem, E dot ds equals to q enclosed by epsilon naught. Now E dot ds, the ds means area is 2 pi r into L and E is E. So 2 pi r L into E equals to lambda L by epsilon naught, because lambda, if charge per unit length is lambda and the total length is L, then the total charge is lambda into L. And from here we get lambda E equals to lambda by 2 pi epsilon naught r. So basically it is this part is constant, so E is proportional to 1 by r. That's what it asked. It varies as 1 by r, where r is the distance from the axis. So it is matching with option C. Option C is the correct option. Moving to question number 9. N identical droplets are charged to V volt each. If they coalesce to form a single drop, then its potential will be. In charging, half of the, oh my god. Okay, so this part is of the answer of the next question. We are considering question number 9. So let r be the radius of each small drop and capital R be the radius of the big single drop. As the volume remains constant, so 4/3 pi r cube equal to n times the 4/3 pi r cube. So this is the volume of the smaller drops, and this is the volume of the bigger drop. And from here we got a relationship between the big radius and the small radius. R equals to n into the 1/3 small r. Capacitance of each small drop equals to 4 pi epsilon naught r. You know this is for a spherical capacitor. We got this formula, 4 pi epsilon naught into radius of this spherical sphere. Okay. Charge of small drop Q equal to C naught into V, 4 pi epsilon naught r into V. Charge of big drop equal to N into Q naught. N times the charge. Charge is always conserved, so this must be the relationship. Potential of a big drop equal to Q by C equals to N Q naught by C equals to N Q naught by 4 pi epsilon naught r. Therefore V big equals to N Q naught by 4 pi epsilon naught r. Now you placed Q naught N 4 pi epsilon naught r B by 4 pi epsilon naught r equals to N r V by into the 1/3 r equals to N to the 2/3 B. R and R get cancelled, so N 1 minus 1/3 equals to N to the 2/3 B. And it is matching with option A. Option A is the correct option. Moving to the last question of this set. An uncharged capacitor is connected to a battery. On charging the capacitor, what would be the option? So you see all the energy supplied is stored in the capacitors. Half the energy supplied is stored in the capacitor. The energy stored depends upon the capacity of the capacitor only. The energy stored depends upon the time for which the capacitor is charged. Now the answer is half of the energy stored in the capacitor and the remaining half is lost in the form of heat which is produced during the process. So option B is the correct option. So, and this is the end. So I have tried my best to provide the solutions in great detail. Irrespective of this, if you have any doubts, confusion or queries, you can comment down below. I will try my best to clarify them all. and any kind of suggestions are always welcome. So this is all for today, guys. If you find this video helpful, please give it a thumbs up, and if you are any visitor of this channel, please subscribe the channel and press the bell icon so that you never miss any update. Keep sharing, keep loving, and keep exploring the wonders of physics. And finally, thanks for watching.